Hello, my name is Charikleia Pappa, and together with Emmanouil Vougioukas, and Nikos Lagaros, we have conducted a study concerning the literature overview of offshore floating wind turbine foundations. We will see the offshore wind turbine categories. The offshore wind turbine is the current prominent way of green energy, and the effectiveness of it is becoming gradually higher. The two categories of offshore wind turbine is the fixed ones and the floating ones. The fixed ones are appropriate for lower depths, while the floating ones are appropriate for deeper waters. There were a lot of attempts of the floating offshore wind turbines optimization, which we will analyze further and check them. It should be mentioned that the world's first offshore wind farm was built in 1991, just a few years ago, and it's expected that by 2030, 205 gigawatt of power generated by offshore wind farms will exist. As of the end of 2020, there was 35 gigawatt installed, two-thirds of which is in wind farms of Germany and China. It is worth mentioning that in 2020, around 80% of the offshore wind turbine foundations were monopiles. The first type of fixed offshore wind turbine foundation is the monopiles, which are currently the predominant type of foundation for offshore wind turbines around the world. This achievement is dedicated to their shape. Their shape is they are circular, and as a result, they are far easier to design and to be analyzed rather than any other type of foundation. Due to its shape, the water resistance is reduced, of course, and they are founded in the seabed. Additionally, since they are one of the oldest ways for offshore wind turbine foundation, this gives them the advantage of acquiring mature supply chains, and they can be mass produced and transported through vessels to be installed. The depth of foundation that they are recommended is 10 to 55 meters. The next is the jackets. The jackets are usually preferred as they are more tolerant of varied geotechnical conditions and can be used in deep water due to the fact that they are stiffer structures and require less steel than monopiles for deeper water locations. On the other side, they are more complex and require labor intense to fabricate and install than monopiles. The depth that they are recommended to be used are 40 to 100 meters. The next type is the gravity-based structures, which are the oldest type of foundation, as their design is based on the counterweight that is needed so as to balance the forces applied on the offshore wind turbine. Due to their stability system, it's needed high quantities of materials so as to achieve this stability, and this is the reason that makes them very expensive and very rarely to be used. The fabrication installation requirements are totally different to other fixed bottom foundations, and the depth that they are recommended is around 15 to 40 meters. Despite it's proven that it's not very cost effective for offshore wind turbines, tripos and tripiles are also a type of offshore wind turbine foundations. The next type is suction bucket, which is usually used for depths around 10 to 15, and they require very specific seabed conditions as they are not drilling deep into the seabed, but they are more surfacial. This has the advantage of being easily removable at the decommissioning of the wind turbines, while the monopiles or jackets are typically cut off just below the mud line. After completing the fixed offshore wind turbine foundations, we will proceed to the floating ones. First of all, let's mention the floating offshore system, which consists of the platform and tower, the blades, nacelle, and hub, the mooring system with tendons, clamp meshes, and the mooring lines, fairleads and anchors, the gearbox, high-speed and low-speed shafts with mechanical brake system, the controller and electricity generator, hydraulics and cooling systems, and the pitch and yaw mechanisms. The first type of floating offshore wind turbine foundation is the semi-submersible floater. This is very commonly used for depths around 40 meters. The structure consists of multiple columns which provide hydrostatic stability and of multiple pontons which provide buoyancy. The above elements are held into place by catenary or tone spread mooring lines, and there with drag anchors which reach the seabed. The motion of the semi-submersible floater is a salient design challenge, but this disadvantage is counterweighted by the fact that it can be used for various depths. The next type is the spar floater. The spar floater is usually used for depths around 100 meters, and it consists of a large spar, which is a draft floating cylinder with a low water plane area. It is designed to keep the center of the gravity below the center of the buoyancy so as it can be ballasted. The spar relates to catenary or toned mooring lines, and these relate to drag or suction anchors which reach the seabed. Comparing the semi-submersible floater with this category of spar floater, the spar floater has better stability and its design is simpler. However, the fabrication, the transportation, and installation are much more challenging because it is a tall structure. The next type is the tension length platform. This is a platform which is vertically moored. It consists of columns and pontons and it's used for depths around 40 meters. Its advantage is the mooring system, which consists of vertical tendons which restrain the heavy motions. Also, due to this, it has stability and can be used in a range of water depths. On the other hand, the tension length platform is laterally compliant and will surge, sway and yaw, while its construction and anchoring system are of high cost compared to other floater designs. The next is the barge platform. The barge platform achieves stability using the air distributed buoyancy, taking advantage of the large water plane area. This type of floating structure is usually distinguished by a rectangular annulated shaped floating substructure with a pool as its center, which diminishes the floater motion by absorbing the wave loads. The suction anchors for floating offshore wind turbine foundations are designed to bear all design loads such as dynamic loads from waves and current and wind turbine generated loads, installation and removal loads from suction overpressure and leveling. Here we can see gathered all types of floating offshore wind turbine foundations, the fixed ones and the floating ones, and we see the depths that they are used as we described previously. We can see that for deeper waters, we can use the floating offshore wind turbine foundation types and the jackets. While there are specific depths after 100 meters that only jackets and the spar type can be used. In order to decide which foundation we will use, there are some factors to be taken into consideration. These are, first of all, the water depth of the site, as we saw at the previous table, the composition of the seabed, the metocean conditions, the proposed turbines, the local fabrication capabilities, the transportation and installation strategies, the operations and maintenance strategies, and the decommissioning concerns. After taking these into consideration, we can see if we need fixed or floating offshore wind turbine foundations and which type of these. Between the two types of offshore wind turbine foundation, between the fixed and the floating, there are some advantages of floating offshore wind turbines. Among others, these are, first of all, that they significantly increase the age of wind farms allowing installations for over 200 meters, as we also mentioned above. They take advantage of the wind resources up to 58%. The wind turbines parts like turbines and bases can be assembled in port and then towered to site for installation, while the maintenance can also be done in port by towering the turbine back to port. We have also the environmental reasons, which is that they minimize the risk of in-cradle repairs. They also concerning the human factor that they're not as visual as on the onshore ones. They certify safe operation under extreme pitch, roll or heave wave motions. There is stability in design and dynamic coupling of traditional and rotational platform motions and turbine motions. We have the dynamic behavior of the mooring lines and the buoyancy to support full weight of turbine and tower of the platform. And the last, the anchoring system, mooring, ballast and buoyancy factors dependent on spar tension or semi-sub. Of course, there are some disadvantages. First of all, the cabling to fix the platforms of the floating wind turbines in planes requires ongoing and throughout inspection and maintenance. The anchors and the cabling may disrupt the sea life, and since the floating wind turbines are towed to site, the possibility of invasive species introduction is increased. There are many improvement approaches that were done for offshore wind turbines. These approaches were referring to several categories. First of all is the mooring and anchoring. They have worked, first of all, to examine the fatigue cracks from corrosion pits on the mooring point. Some others tried to simplify the anchor chain soil interaction into equivalent stiffness and damping at the embedded point of mooring line, so as to develop a fully coupled numerical analysis model of a floating offshore wind turbine, and they include aerodynamic, hydrodynamic, and mooring and anchoring foundation. There are many. Some others are that they demonstrate a model of precision in predicting aerodynamic performance, motion response under wind and wave conditions. And these efforts most of them have very significant results. Another sector of improvement that many people have worked on is on structural design and damping. They tried transformation of a catamaran into a platform for tidal energy. This was tested only for small-scale projects, and the results showed that the side-to-side movement could only be avoided by external control methods. Some other tried to approach fully submersible platforms, which combine the advantages of a semi-submersible and spar platforms. This concept employs inclined side columns that are used to increase the water plane and thus the moment of inertia while minimizing the draft and stress on the support structure. A fully submersible floating platform is similar to a submersible one, but the middle parts of the columns are inclined outwards, while the upper and lower parts remain upright to connect to the center column via a set of cross braces and pontons. Others focused on the damping, and more specifically on the integration of a tuned mass damper for the TerraSpar floating offshore wind turbine that shows commendable stability and analysis of the vibration suppression effects of different TMDs on the wind turbine system. Others have introduced an analytical model of dynamic responses for one operating offshore wind turbine supported by bucket foundation based on a multi-degree of freedom vibration theory. Many others have also done theoretical analysis and model test of the bucket foundation with and without buckets was performed. The frequency domain of the two models were obtained and compared via cycle loading tests at different frequencies. Others have focused on materials. They have introduced the concrete field steel tubular jacket. It is a novel hybrid steel concrete structure used in offshore wind turbine foundations where compression, bending, and torsion loads are the primary considerations during the design process. Others have given proof that the cell thickness could be reduced significantly by introducing the stiffeners, which can decrease the weight of the hull and lower the cost. Others have approached the probabilistic corrosion and fatigue evaluation model for bolts, accounting for multiple failure models. Having attempts for improvements in the environmental interaction is also very important. We have seen the reliability assessment method in order to evaluate the performance of turbine platforms in offshore environments, taking into consideration the platform's motion modes and waves frequencies, as well as the platform's degrees of freedom, time response, and of these motions, and accounting the uncertainties in wave characteristics, wave impact directions, and wind effects, so as to result in an optimized platform design and decision-making process for floating wind turbine platforms as far as safety and structural stability is concerned. Many others were done for environmental interaction. We will proceed with the next. Some were focused on control strategies, so they have checked the examination of the simultaneous optimization of a floating wind turbine platform and its feedback-based control strategy. Others have proceeded with the presentation of several control co-design optimizations of floating offshore wind turbines using the newly introduced wind energy with integrated servo control framework. And some of the others is that they have proposed a novel failure mode and effect analysis schedule, namely correlated failure mode and effect analysis to identify critical failures of floating offshore wind turbines with correlated failures. We can see that the attempts to optimize the offshore wind turbine foundations have shown a big peak and increase in the year of 2024, while all the previous years since 2012 there was several attempts, but 2024 was a big peak. We lead now to the conclusions, and we can see that making a comparison between all the types, we can see that monopiles can be used for depth between 10 to 15 meters, and this is the reason to deepen more and suggest solutions and directions to use them in deeper water. On the other side, jackets are more complex and require labor intense to fabricate and install than monopiles. This gives space for further research, so as their fabrication becomes approachable and more convenient also for this case. The gravity-based structures require high quantities of materials to achieve the stability, and this is the reason that makes them very expensive for deep water sites. And as a result, a material approach to simplify it would pave the way for a more efficient use of it. Also, the tripods and tripiles are not regularly used because they are not cost effective for offshore wind turbines. More research is needed so as to reduce their cost and enter them into the floating wind turbine sector. Additionally, the section buckets require very specific seabed conditions as they are not drilling deep into the seabed. This gives space to rethink their way of foundation. For spar floaters, the fabrication, transportation, and installation are more challenging because of its tall structure. Focus on the shape and transportation could lead to solutions which could make them more convenient in use. And the tension leg platform is literally compliant and will surge, sway, and yaw, while its construction and anchoring system are of high cost compared with other floater designs. This triggers the chance to study further the anchoring system. Thank you for your attention.